Well, here we are, section 14. In this, we're going to take a brief look at the mechanics of fluids. I'm using the word fluid here in its most general sense to mean anything which will flow, a liquid or a gas, in other words. Like many of the things that we spend just a few days on in this course, you can take an entire course on fluid mechanics. This little treatment I'm going to give you here just scratches the surface. Well, first of all, as soon as I swing the camera around at the blackboard, I'll write down the definition of density. It's mass per unit volume. That's a quantity that frequently comes up when you're talking about a fluid. Now, fluid mechanics can, well, like mechanics in general, can be divided up into statics and dynamics. Statics is when you're talking about objects that are remaining at rest. Dynamics is stuff that's moving around. Hydrodynamics would be the study of moving fluids. A lot of textbooks do it the other way around. They start with hydrostatics and have hydrodynamics at the end of the chapter. But I kind of like to start with hydrodynamics because then when you want to talk about the static case, you just set the velocity of the fluid equal to 0 and there's your static stuff. Anyhow, we are going to restrict ourselves to a special case. So this is a great sentence, I think. Try saying this to somebody at a party sometime and see what sort of reaction you get. We're going to assume steady, streamlined flow of an incompressible, non-viscous fluid. Steady just means that as time goes by, things don't change. Streamline. There are two basic types of fluid flow. Streamline means non-turbulent fluid flow. This is supposed to be a cross-sectional view of a pipe. So maybe you've got a 1-inch diameter pipe here, and then there's like a reducing coupling, and then there's a 1/2-inch pipe going off to the right there. And if you have streamlined flow, that means, like if it's water flowing through this pipe, every particle of water that flows through point A continues downstream along this same streamline that I've drawn here. And every particle of water that passes through point B goes on to follow this streamline, and so on. Turbulence, on the other hand, is much more, well, actually, the word is chaotic. There is a branch of mathematics called chaos theory that's involved in dealing with turbulence. If one particle of water passes through point A and a little while later is over here, some other particle of water later passes through point A, could be anywhere when it gets over here, much more complicated. And the transition from the one to the other is actually quite abrupt. If you're making your fluid flow through the pipe slowly, it's going to be this well-behaved streamlined flow. And as you gradually open up the valve so that the fluid goes faster and faster, the shift to turbulence will be quite abrupt, and there will be a noticeable increase in the amount of resistance to pushing the fluid through the pipe. Or it doesn't even have to be in the pipe. I've got another photo, got to raise that up. Got a column of smoke in this photograph, like maybe somebody's just blown out a candle, and you know, you get that column of smoke coming off it for a little while before the wick completely cools off. Or it could be a cigarette sitting in an ashtray. So what you typically see in a case like that is, rising up from the source, you get this well-behaved column of smoke And then at a certain point, a foot or two above the source, right here in the photograph, you get the transition. So whereas before, down here, the smoke is just streamlined flow, above that you get all these eddies, all of these vortices. It's really rather nice photograph, actually. So we are going to restrict our attention to this. Streamlined flow is relatively simple. It's been well understood for close to 300 years. Turbulent fluid flow is very much still a topic of current research today. A lot of progress has been made in the last several decades as very powerful computers became available. And also, I mentioned that chaos theory is a relatively new branch of mathematics, and that has shed some light on things also. So, I guess that's right, I didn't have a book under this before. Go. Steady, streamlined flow of an incompressible. Well, a couple minutes ago I got done, I was saying that we could be talking about a liquid or a gas, but actually, if you want to get specific and use the equations I'm going to be writing down, liquid. Gases are compressible. If you have a balloon full of air, you can get it between your hands and squish on it and it gets smaller. Whereas water, for example, well, it's not literally incompressible, but you have to get something like 3 or 4 miles below the surface of the ocean before there's enough pressure to make water occupy 99% of the volume that it would at the surface. Okay, so as long as you're not trying to go to too many decimal places, liquids, water or whatever, water is incompressible. Non-viscous, like it says down here, viscosity is the internal friction inside of a fluid. Imagine 2 drinking glasses and you fill one of them with water and you fill the other one with honey, and then turn them both sideways and watch what happens next. Well, the water's going to pour all over the place. The honey's going to take its time. Honey is much more viscous than water. We're going to assume no viscosity at all, which actually makes it impossible to have any kind of a pressure gradient along your pipe here. So a lot of assumptions, some of which are unrealistic a lot of the time, but that's, for just a quick little 1-week treatment at the end of the course, that's the special case we're going to stick to. So after I write down the definition of density, which I really will do eventually, just watch, what I'm going to do after that is write down a couple of equations. Well, more than write them down, I'll explain why they're true. Imagine you've got a fluid flowing through a pipe, and you want to compare what's happening at one point to what's happening at another point. Well, these 2 points might differ in several ways. There might be a difference in elevation, H1 and H2. There might be a difference in the cross-sectional area of the pipe, A1 and A2. There could be a difference in the speed that the fluid, well, if we're assuming it's incompressible, I might as well call it water. I mean, it could be mercury or alcohol or something like that, but the speed of the water here is V1. The speed of the water over here is V2, or this script V that I've written anyhow for velocity. I'm also going to be talking about volume at times. So we'll use this capital V for the volume of this little bit between here and here. Or it would be the same as the volume as this little bit, between the solid line and the dashed line over here, that little cylindrical volume. So those will be the equation of continuity and Bernoulli's equation. And that will be enough to keep me busy for a little while over here. There, I think. Okay, first of all, density. The symbol used by most books for density is the Greek letter rho. A lot of people want to call it P. It's a Greek R, not a Greek P. Greek P looks like that. Try and make it look different from a P somehow, because in a matter of just a few minutes here, I'm going to be writing down an equation that contains both R for density and P for pressure in the same equation, and you want to be able to tell the difference between them. Mass per unit volume. Lead has a high density, styrofoam has a low density. Same amount of volume contains different amounts of mass depending on the substance. Okay, so the equation of continuity. Remember in the diagram over there on the handout, you had, maybe I should sketch it just quickly. You had something that looked kind of, which end was bigger. So you've got this piece of pipe, and we're interested in comparing what's going on here to what's going on here. If you consider the section of pipe between those 2 points, because the fluid is incompressible, the volume that goes into the one end has to equal the volume coming out of the other end. If you just picture yourself standing in your backyard with a garden hose, okay, a hose that's full of water. And you've got one end of the hose, and maybe you've got a friend who's holding up the other end of the hose at the same level. If you don't have a friend and lay it on the ground, all the water will run out. So this hose is full of water, and you've got a funnel and a pitcher, and you pour 1 quart of water into that hose. As you do that, 1 quart of water has to run out of the other end of the hose, because the hose was already full of water. You put more in, where's it going to go? It's got to come out the other end. Now, a compressible fluid like air, you could squish more in there by increasing the pressure. But if you're assuming an incompressible fluid, then the volume that goes into one end has to equal the volume that comes out the other end. So if you see, the idea is the fluid moves from there to there in a time delta t. And over here on this end, that's the distance that the fluid moves in a time delta t. So this much water goes in the one end, that much water comes out the other end, and they have to be equal. The volumes of these little cylindrical regions I've sketched. I'm not quite sure if it's grammatically allowed to try and make a picture plural, but I've done it anyway. So the volumes of these things, these little cylindrical sections of water, are equal because the fluid is incompressible. Now, everything's labeled on the thing on the handout there, but the distance that the fluid moves in a time delta t, this distance I've labeled with the little arrow here, that would be v times delta t. Distance equals speed times time. So if you've got a chunk of fluid that goes between the solid lines at the beginning of delta t, and it goes between the dashed lines at the end of delta t. This end is moved v1 delta t, this end is moved v2 delta t. The volume of a cylinder is its length times its cross-sectional area. So, moving this over a little bit. Cross-sectional area times the length of this cylinder, cross-sectional area times the length of that cylinder, the volumes have to be equal. Delta T drops out, you divide both sides by delta T and it's gone. So, you could write the equation of continuity as A1V1 equals A2V2, or I believe the way I put it on the formula sheet is just to say A times V is constant. A times V multiplies out to give you the same thing at any point along that pipe. So if you compare two different points, that'll be, or if you compare 7 different points, they'll all be equal for that matter. And let's be clear about the letter V. That's V for velocity, not V for volume. Now, this and also Bernoulli's equation, once I get that written down, they apply exactly only for incompressible fluids, but you get the same general sort of behavior if it's a compressible fluid. In other words, compressed air going through a pipe instead of water going through a pipe. Yeah, it acts more or less the same way. It just gets a little more complicated. For example, this equation, if it's compressible, instead of A times V is constant, it becomes A times V times rho is constant. Okay, there'd be a factor for the density also. If the density is always the same, then that part drops out. Typical consequence of this, well, again, imagine yourself in the backyard with a garden hose, only this time the hose is hooked up and there's water flowing through it. And you're, I don't know, watering the roses or the tomato plants or something, but it's a hot summer day and your friend is right over there and you're feeling kind of mischievous. You can put your thumb over the end of the hose and it makes the water squirt out real fast, and you get your thumb, or you get your friend with the hose, and then probably chase each other around the yard for a little while or something. But you see, by covering over the end of the hose with your thumb, that makes the cross-sectional area that the water passes through get a lot smaller. Okay, if this goes down, this has to go up to still multiply out to the same thing. So you give it 1/10 the opening to pass through, and it'll go through it 10 times as fast. And so that's what that's all about. If you want to just appeal to common experience instead of some mathematical derivation, this is put your thumb over the end of the hose and it makes the water squirt, also known as the equation of continuity. Then there's Bernoulli's equation. There was a whole family of Bernoullis, actually. They were Swiss. This was Daniel Bernoulli, who came up with this in 1738. They didn't actually get along with each other very well. Thanksgiving at their place was probably kind of uncomfortable, except I'm pretty sure they didn't do Thanksgiving in Switzerland in 1738. They probably don't do Thanksgiving in Switzerland today, actually, but Bernoulli's equation is based on the work energy theorem. Okay, we're going to take the work energy theorem and apply it to the water flowing through this section of pipe that I drew on the handout over there. And let's start out with the work term. On the picture, maybe I should just point you at the thing again here for a moment. So we are interested in the chunk of water that originally goes from this solid outline to this one at the beginning of delta t, and at the end of delta t, it's moved a little further to the right, and that chunk of water begins here and ends over there at the dashed lines instead. The work done on that chunk of water as it moves is the work done by the water that's beyond it on either end, okay? The water that's off to the left of it is helping to push it along with this force I've called F1. Well, it follows from the definition of pressure. If P equals F over A, then F equals P times A. There is also work done on it by the force exerted on it by the water that's ahead of it. That water, because of the water pressure, it's pushing back on our chunk of water in a direction that opposes its motion with this force here. And so work is force times distance. The work done over here would be this force times the distance it pushes through, which I call delta x1. And the work done over here is, well, this one would be negative because it opposes the motion, okay? There's that cosine factor in the definition of work. and the water is being displaced to the right, but the force pushes to the left, and it gives you a minus sign. Anyhow, force times this distance, F2 delta X2. So let me get that written down. That's the work done by the force that's to the left of our chunk of water. This is the work that's done by what's off to the right of our chunk of water. And again, the minus sign comes from the cosine factor that's in the definition of work. Over here, it's cosine of 0 degrees, which is 1. As it shows on the diagram that I was pointing you at a minute ago, the force is the pressure times the area. Well, as I already mentioned when I was back up in here, the volume of a cylinder is its cross-sectional area times its length. And that occurs again here, okay? Cross-sectional area times the length of this little chunk over here, that A1 times delta X1, that's this volume here, and A2 times delta X2, that's this volume over here. And the whole idea of this other equation was that those are equal to each other, so I don't need to call them V1 or V2, they're both just V. Being careful to label that as being volume. So, if I can squeeze this in on the edge, we have a common factor of V. The work would be P1 minus P2. If I factor out the V, the difference in pressure between point 1 and point 2 times the volume of my little chunks of water, that's the work done. So, having decided that, let's write down the work energy theorem. Energy is kinetic plus potential, of course, but what's going to be convenient is, point you at this again. For the initial energy, I want to break it up into two parts. Initially, my chunk of water goes from my thumb over to where the pencil is here. The water is between those solid lines. The total energy of that water would be the energy of this little part of it from the solid line to the dotted line, plus the energy of the rest of it. And for the final energy, when the water goes from the dashed line to the dashed line, the energy of that would be the energy of this little part between the two lines, plus the energy of the rest of the water. I'm going to write that down. So if the mass of those little parts is m, those little cylindrical regions, the initial energy is the energy of the mass on the left plus the energy of the rest of it. And the energy final is the energy of that little mass on the right plus the energy of the rest of it. And the reason I wanted to split it up that way is the energy of the rest of it stays the same. One of our assumptions here is steady. So nothing has changed between initial and final. And so that is equal to that. And if I subtract it from both sides, it's gone. The energy of that little mass on the left would be its kinetic plus potential. Work is the thing I had written back over here. And the final, kinetic plus potential. Divide through by the volume. So what's going to happen if I divide through by the volume is every place, I'll finish writing it down in a moment, but every place there was an M, there will be an M over V, and that's the density of our fluid. Okay, what this does is it eliminates references to those little chunks of water that I sort of arbitrarily drew on my picture and replaces it with something which is a basic property of the fluid, its density. So every place there's an M, it's going to become M over V, and the V will disappear from that term. V over V is 1. Capital V for volume, script V for velocity. We're almost there. Mass per unit volume is density. And then the other thing I'm going to do is I'm going to add the P2 to both sides so that it's collected together with all the other things that have 2's on them. And we end up with this. So we have another thing which remains the same if you compare any points along this pipe. A little more complicated than just A times V. This time it's the quantity of pressure plus 1/2 rho V squared plus rho GH, which will be the same at one point as it is at any other point. And the way that's written on the formula sheet is like this. And that's Bernoulli's equation. And it's time to run through an example. So we have this little tube with kind of a narrow spot in the middle. Looks a lot like this glass tube here that I'll be using in a moment, or maybe more significantly, hold on a second. As far as practical applications go, this is a carburetor off of a lawnmower I used to have. Automotive carburetors are a good deal more complicated, but use the same basic principles. Maybe I should pull this back a little bit. If you look in, well, I got to open up the throttle so you can see in there, but maybe it works better on the other side. Yeah, that's a good view. Notice, you see, air flows through here, okay? Every time the piston moves down the cylinder, it sucks in air behind it, so you've got a draft blowing through the carburetor. Well, notice they're right in the middle of the carburetor. It gets a lot narrower. And can you see, if I get it at the right angle, it doesn't show up very well, but anyhow, that's the same thing as this glass tube here, which is a little easier to see inside of because it's made out of glass. In the carburetor, this bowl here is full of gasoline. And well, I'm getting a little ahead of myself, but this type of arrangement is called a Venturi tube. And we're given some numbers. Now, in this example, the fluid flowing through the tube is water because, like I said, the equations are only exactly correct if you have an incompressible fluid, although you get the same general sort of behavior if the fluid is air. But in this example, it's water. So over here at the end, the water shoots out into the atmosphere, and therefore the pressure at that point, which has for some reason gone out of focus, but no, it's back. Atmospheric pressure. Standard atmospheric pressure is 101 kilopascals. And here I've only got 100 kilopascals, but you know, that varies a little bit with the weather and the altitude, and that's a very realistic number, and it's nice and even, so we'll go with that. Cross-sectional area of the tube here is only 1/3 of what it is on the end, and the question is, if we know the speed the water shoots out over here, well, the final thing we're going to try and determine is the pressure, but the first step is to get the speed in there. It's going to be a two-step process. Bernoulli's equation is the one with pressure in it. So that ultimately is what's going to give us our answer for the pressure. But Bernoulli's equation also contains the speed, and so we have to figure out the speed so that we know everything in Bernoulli's equation aside from the pressure. So that's the general idea. Accidentally pushed the wrong button there. Sorry about that. I'm going to blow through here. And if the pressure is high in here, which is what a lot of people seem to expect, then if I blow hard enough, it ought to make bubbles come out of the end of the hose down here, right? Let's see what actually happens. I don't know how well that showed up in the video because I didn't do it looking at the monitor. Yeah, I think that showed up pretty well. There was this whole mist of water that came shooting out of here. Like I said when I first started talking about this, this thing is a carburetor. You've got a bowl full of gasoline, right there. You got a bowl full of gas. The fuel line, actually, yeah, This has gotten, well, you know, fuel line attaches right here. On a lawnmower, there's no fuel pump. They just have the tank up high so that the gas will run downhill through a hose. Go in there. There's a little float in there like you have in a toilet tank that maintains the gasoline at a certain level. And when you're looking in there, if you look at just the right spot, you can see just a little tiny narrow, it's about just a little bigger around than a pencil lead, but there's a little tube that comes up into the airstream out of the bowl of gasoline, and it does exactly what you just saw here. As the air blows through the carburetor, you get a low pressure where the thing is narrow, and that draws the gasoline. Well, I mean, if you want to split hairs, it's actually pushed by the higher pressure that bears against the fluid here. But if you want to think of it that way, it gets sucked up the straw there into the airstream, where the fuel breaks up into lots of little droplets, just like you saw the water doing on this thing. And that's how you get your air-fuel mixture. Okay, the fuel gets mixed with the air that's moving into the cylinder, and it goes in there and it burns. Or what amounts to practically the same thing also is a paint sprayer. You got a can full of paint instead of a can full of gasoline. You hook it up to your air compressor. You've got the air blowing through there. It sucks the paint up into the airstream, and same kind of thing going on. The fluid doesn't necessarily have to be confined inside of a pipe either. This Bernoulli effect is one of the factors, it's not the only factor, but it's one of the factors responsible for the lift on an airplane wing. Seen in a cross-sectional view, an airfoil looks kind of sort of like that. So you've got this, well, relative to the airplane anyhow, you've got this air approaching the wing from the front, and this flows underneath like that, and this flows over the top like that. And like many things, if you get into it in detail, the story gets very complicated. But as sort of a crude idea of what's going on anyhow, this air has to get to the back edge of the wing in the same amount of time as this air, but it has to cover a longer path to get there, so this moves faster. And just like we saw in this example with the Venturi tube, where the fluid goes faster, the pressure goes down. So you have a region of lower pressure above the wing and higher pressure below it, and that's part of what supports the airplane. Anyhow, basically, Bernoulli's equation, if you want to distill what's going down into words instead of an equation with subscripts and Greek letters and things like that, the rho GH term says if there's a difference in height, all else being equal, the pressure increases as you go down. And we'll look at that in a little more detail in a moment. But it's like if you're scuba diving, the farther down you go in the ocean, the greater the pressure on you. So there's that factor from the rho GH terms. The pressure increases with depth. And then from the 1/2 rho V squared terms, pressure decreases with speed. Okay, the faster, this is among the factors that can cause a chimney to draw also. It makes the gases, even if you don't have any fire in the fireplace, you'll still get some air going up the chimney if there's a wind blowing across the top. And it's the faster the wind goes, the lower the pressure there gets. So there's a trade-off between the speed of the fluid and the dynamic pressure, and that's the other thing that's going on in Bernoulli's equation. So how far down are you in the fluid, and how fast is the fluid moving? And that's kind of in words what's behind the equation. So the next thing on the handout there, it says hydrostatics, fluids at rest. And the first thing on the list says the variation of pressure with depth that I was just talking about. So fluids at rest. Hydrostatics. If the fluid is at rest, if the fluid is at rest everywhere, that zeroes out the kinetic energy terms. Rearranging a little bit, we get that. Factoring out a couple of common factors. And writing that a little bit more compactly. There is how the pressure in a fluid varies with depth. Maybe I should label it. If you're a scuba diver, and you're going deeper and deeper below the surface, well, all that water sitting on top of you weighs something. So the farther down you go, the more weight is bearing down on top of you. And so that's why the pressure is increasing. And this is how much it increases. So right at the very bottom of the page, it says, oh, I suppose maybe I'll point you at it for a moment. Example number 2, find the pressure, here. Now it's a little fuzzy, but I think you can make it out. It says, find the pressure 30 meters below the surface of a lake. I made it a lake and not the ocean because the density of fresh water is available on your reference handout, whereas the density of salt water is a little bit heavier because of the salt mixed in it. And you don't have a convenient place to look that up. Although if you actually care, I think it's about, this is from memory. I might not have it quite right, but I think seawater is about 1.03 grams per cubic centimeter instead of 1.00 like fresh water is. In other words, 1,030 instead of 1,000 kilograms per cubic meter. Anyhow, I'm going to draw a little picture just to keep everything straight. There's the surface of the lake. question is asking us about a point that's 30 meters down. Well, here's the thing that might be a little tricky. Normally, when people go out in a boat, they talk about the depth. People, you know, it's sort of a natural and convenient thing to do, to put yourself at the origin. Say, I'm at 0, and how far is that down from me? But the way I've written all this stuff, for the sake of being consistent with the notation used for everything else throughout the book, is in terms of height rather than depth. Okay, so if you're at, in other words, for the delta H in this thing, it's not 0 and 30. You could do 0 and negative 30, that'd be all right. But, well, I'm not that fond of negative numbers. I mean, I can deal with them if I have to, but I'm going to say that height down here is 0, and okay, so it's not 0 and 30, it's the other way around, 0 and 30, because H is for height, not depth. At the surface, you have atmospheric pressure. Finding the pressure down here is what the question wants me to do. So from over there, the difference in pressure between those 2 points is minus rho g times delta H. P2, you know, delta P is P2 minus P1. So delta P is P2 minus P1. I added P1 to both sides because the pressure here is what I'm trying to find. Since the question doesn't say anything to the contrary, I'm going to assume standard atmospheric pressure, which I can look up in the formula sheet. And if anybody can't figure out where, send me an email or something. For the other numbers, density of water, 1,000 kilograms per cubic meter, G 9.8 meters per second, H2 minus H1, 0 meters minus 30 meters, minus cancels minus. You should be adding to the pressure as you get farther and farther down. If the pressure seems to be getting less as you get deeper, you've probably forgotten a minus sign somewhere. So minus cancels minus, and you're adding this to that, and it comes out 3.95 times 10 to the 5th. I think the basic, if I remember right, the basic rule that divers use is 1 atmosphere worth of pressure for every 33 feet. That would be for seawater. I guess it would be 34 feet in freshwater, if I'm remembering my numbers correctly. Well, we are actually not that far from the end of the unit here. Section 14 is not the longest one in the course. So I think I'll just keep right on running here and do the whole thing in one recording. And if you don't want to sit in one spot for that long, Well, like I've said before, you can, it's a video. You can watch this 5 minutes at a time if you want to. Just start it and stop it and pay attention to where you left off and come back later. We have an example, a version of something called the hydrostatic paradox. We have here 3 glasses of water, all of which have the same amount of area on the bottom. But because the upper parts are shaped differently, there are different amounts of weight for the amount of water that's in there. And you're supposed to compare the pressure at the bottom of those 3 glasses. And I usually turn around and say to the class, what do you think? And after a moment when nobody really wants to say anything, somebody finally gets brave. And actually, more often than not, they get this one correctly, which is, I'll write this down in a moment, but the correct answer is that it's the same. Pressure is a function of depth only. If you look back at these equations I've been flinging around, like right there, the one for there's no other variable besides the depth. So whether you're a foot below the surface in a drinking straw full of water or a foot below the surface in Lake Ontario, it's the density and gravity and the fact that you're a foot below the surface, and that's all there is to it. What you're supposed to be deceived by here is the false way of looking at this is to say, well, let's see, pressure is force per unit area. I've got the same area. There would be the most force here where there's the most weight to support, and the least force here where there's only a little bit of water to support. So pressure would be greatest here and least there, and people have even tried to design perpetual motion machines based on this principle. If you had a reservoir of water shaped like this and another reservoir of water shaped like that, what you could do is run a tube from the bottom of this one to the bottom of that one, and the water in that tube would flow from the higher pressure here to the lower pressure there, and as water is forced into this, it would go up, and you could have some sort of a trough for the water to flow back over here from this one back into this one, and you could maybe put some sort of a little water wheel in that trough, and that could generate electricity or grind a grain or do some useful work for you like that, and it would just run forever without any kind of fuel, right? Yeah, unfortunately, conservation of energy says perpetual motion machines don't work, which doesn't stop some people from continuing to try. But, well, newsflash, the world is full of people who don't know what they're doing. But anyhow, the correct answer is that the pressure is the same. You see, the force from the walls is normal to the surface. So on these walls that are slanted outward, the force pushing back from the walls of the glass have an upward component that help to support the water. The full weight of the water doesn't bear down on the bottom. Some of it's supported by the sides. And same thing here, where this runs this way, the force from the walls has a downward component that helps to push, it's transmitted through the water to the bottom, even though there isn't as much weight to support, it all works out the same. So guess I'll write that down over here. Just a wonderful little thing my wife spotted. So I don't do Facebook myself, but my wife seems to live on the thing. And she handed over her tablet to me one day a few weeks ago. And somebody had posted something that says, well, maybe someday there'll be a zombie apocalypse. But right now, I'm more worried about a stupid people apocalypse. And people who want to build perpetual motion machines are probably one of the less dangerous examples of that. Anyhow, 14.3. Pressure is the same at the bottom of all three glasses. P, the pressure, depends on depth only. The question says all three have been filled to the same depth. End of story. Next, we come to Pascal's principle. And it says over there, well, let me justify it, and then maybe I'll point you at the thing over there again. But we had, like in the previous example, it said P2 equals P1 minus rho G delta H. So let's say you've got a fluid enclosed in some sort of vessel, okay? If you've got something out in the open, like a glass of water, and you try to apply some pressure to it, it won't work. The top's open to the atmosphere, and where it's in contact with the atmosphere, you'll have atmospheric pressure. But if the fluid is enclosed in some sort of a system, such as, well, for example, the brakes in your car, the brake fluid is not open to the atmosphere, well, unless you forget and leave the lid off the master cylinder. The brake fluid is not exposed to the atmosphere anywhere. It's all enclosed within a system of tubes and cylinders, okay? So if you apply some pressure to the fluid at a certain point, such as the master cylinder, okay? You step on the brake pedal, and the motion of the brake pedal is transferred to the motion of the piston inside the master cylinder, and it pushes against the brake fluid, creating additional pressure. If you create pressure at a certain point in a fluid, such as point number 1 here, it says, if you increase P1, then the thing to notice is P2 increases the same amount. If you increase P1, because rho GH isn't going to change, you know, gravity is still the same, the density is still the same, where the 2 points are located relative to each other is still the same. So if you go adding 5 pounds per square inch on one side of the equal sign, you got to add 5 pounds per square inch on the other side of the equal sign if the two sides are still going to equal each other. So if you apply a certain amount of pressure at the master cylinder, the pressure at each of the wheel cylinders goes up by the same amount. And by pressurizing the brake fluid, it makes the brake pads push against the rotors, and that creates friction and stops the car, and that's how the brakes work. The regular service brakes, anyhow. The emergency brake works with a cable, but this is called Pascal's principle, okay? The idea that pressure applied at any point in an enclosed fluid is transmitted, you know, the same amount of pressure to everywhere else in the fluid, That's Pascal's principle. As stated on the note packet page here. It's probably time for me to raise that up a little bit. Pascal's principle. Additional pressure applied to an enclosed fluid is transmitted to every point in the fluid. Pascal's principle is the basic physical principle at work in any kind of hydraulic equipment. And a lot of stuff is hydraulic. Like I said earlier, the most common around the house type of example is probably the brakes on a car. Cars have had hydraulic brakes since the 1930s. But you know, construction equipment is full of hydraulics. If you want something a little more warm and fuzzy rather than, you know, a backhoe or a bulldozer, a number of years ago, we were on vacation in Vermont and we went to the visitors center for the Vermont teddy bear factory. And the first step in making a teddy bear is you take a piece of fabric and you cut a teddy bear shaped piece out of this sheet of fabric. Well, they don't have a room full of people sitting there with scissors in their hands doing this, aside from the fact that it would be just terribly tedious work. I mean, you'd have, you know, people committing suicide and things like that. It's also an awful lot cheaper if you can automate things. So the way they do it is they lay out like 10 or 12 layers of fabric on a table, and then they've got, it's like a cookie cutter. It's shaped like a teddy bear, this really sharp cutter that's pushed downward through the fabric by a hydraulic press, and then you've cut out your teddy bears. Well, of course, they have to take the fabric then and stitch it up and put the stuffing in it and all of that, and there's some of that's done by hand. But anytime you want to create large forces like that, hydraulics are a good way to do it. The lifts in a garage where, you know, they pick up your car so the mechanic can get under there and look things over. That's hydraulic, and so on. Well, actually, I guess it's partly pneumatic in a garage. But the way the terminology works is if this is a liquid in here, it's hydraulic. If you're using compressed air, they call that pneumatic instead. Anyhow, we have something here like a simplified hydraulic jack. Like if you go to Tractor Supply and you buy a little hydraulic jack that you can use to change the tire on your car or something. Well, it actually has a lever over here that gives you an additional mechanical advantage, and it's kind of convenient. And there's check valves to let the oil only flow in one direction if you set it that way. But if you strip it down, you know, ignore all of that stuff and just strip it down to the basic idea to illustrate Pascal's principle. You've got a little cylinder with a little piston in it, seen here in cross section. If you were looking down from above, these would be circular, okay? But you're looking at it from the side here. So a little cylinder with a little piston in it, a big cylinder with a big piston in it. The space in between is filled with some sort of a fluid. If you go back to the roots of the word hydraulic, hundreds of years ago, people were originally talking about water, actually. But what would typically be used today is, well, I used the word oil because it's, you know, a nice, simple little three-letter word, but hydraulic fluid is not exactly oil, like, you know, like olive oil or something like that, but it's an oily substance similar to brake fluid, is what you have in there. So you push with a force. See, there's a heavy thing here you want to pick up, like your car. Okay, you have to get one of the wheels off the ground to change a flat tire. So you put a little force, 200 newtons, that's less than 50 pounds. You put a relatively small force on this little piston. The little piston pushes on the oil pushes on the big piston. And now here's the thing. Pascal's principle says it's not exactly force that's transmitted from the one piston to the other. It's pressure. And pressure is force per unit area. So if this piston is 20 times bigger than that piston, this force will be 20 times bigger than that force in order to still have the same ratio. Force per unit area, F and A, both 20 times bigger, you still have the same force per unit area. So little force divided by a little area, big force divided by a big area, same pressure. That's how a hydraulic press multiplies force for you. I should write down the details. It's not a terribly lengthy calculation. Pascal's principle. The additional pressure on the one piston equals the additional pressure on the other piston. I called it delta P because, you know, before anybody started pushing on anything, you already had atmospheric pressure. And then, you know, you push on it and that creates additional pressure. F1 over A1 equals F2 over A2. So therefore, I guess I called the one I'm looking for F2. That would, you know, multiply both sides by A2 and you've got this. The ratio of the areas times F1. Now this one just gave the areas. If I give the radius or the diameter of the piston, you'd have to use pi r squared to figure out the radius, or figure out the areas, but here I just kept it short and sweet. And A2 is 10 centimeters squared. A1 is 0.5 square centimeters. Once again, as in that example I did a while ago with the equation of continuity, non-standard units, the SI system would require that you use square meters rather than square centimeters, or in that other one, it was even worse, I was using square inches, but they cancel each other. So since they go away anyhow, it doesn't matter what they were. It's a 20-to-1 ratio, that's going to be the same in any system of units. This might seem like you're getting something for nothing. You put in 200 newtons and you get out 4,000 newtons. And incidentally, a hydraulic press is not the only device that will do this. There are several others that will multiply force in the same way. A lever, for example, if you're prying on something and you've got the pivot point way down close to the thing you're prying on, the force from the one end of your lever is going to be a lot more than the force you're pulling on the other end with. Or, you know, block and tackle system or a screw. There's several different ways of multiplying force like this. But you see, there is no such principle as conservation of force. Force doesn't have to be conserved. There's nothing wrong with putting 200 newtons in and getting 4,000 newtons out. What has to be conserved is energy, and you don't get any more work out than what you put in, whether it's this or a lever or a block and tackle system or whatever it is. You see, as this little bitty piston slides down this small cylinder, just a small amount of oil is displaced. And when that little bit of oil flows in behind this great big piston over here, it goes up just a small distance. Or it's like if you've ever used a scissors jack to change a tire on your car, you know, you're working the jack and your hand goes that far and the car goes up about that far, okay? So what goes on here is you've got a little force times a big distance, and over here you've got a big force times just a little distance. This moves a much shorter distance than this one does. So you don't get any more work out than what you put in. And so energy is conserved. The last thing on the list, the last topic in the course, buoyancy. Buoyancy is the effect that makes things float. Whether you're talking about a person floating in a swimming pool or a helium balloon floating in the atmosphere, it's held up by buoyant forces. Anything, let me point you at the blackboard again. Anything that's immersed in a fluid, whether the fluid is water or air or any other fluid you want to talk about, anything immersed in the fluid feels a net upward force from the surrounding fluid. The reason is what I was talking about a couple of panels over to the left there. It's because pressure is a function of depth. Buoyancy. So let's say you've got a let's say we're in a swimming pool, okay? I'm standing here with my mask and my snorkel talking about all of this. And underwater here, I have some object. The water on top of it presses down. T for top, the force on the top. Be the pressure on the top times the area of the top. Force on the bottom is greater than the force on the top. This would be the pressure on the bottom times the same area. I'm assuming the area of the top is the same as the area of the bottom here. Because pressure increases with depth, the pressure down here is more than the pressure up here, and therefore the force pushing up on the bottom is less than the force pushing down, or is more than the force pushing down on the top. Force on the bottom is greater than the force on the top because the pressure on the bottom is greater than the pressure on the top, and that's where buoyant forces come from. How much force is pushing upward on this thing? How large is the buoyant force? Well, what if this object that I have immersed in water is more water? What if I'm just considering a chunk of water surrounded by more identical water? There's my chunk of water. And outside of it is more water. Well, this chunk of water weighs something. And the surrounding water creates an upward force on it that I'll call B for buoyant force. This force B would be the resultant of the two that I drew here. This minus that is equal to B. That's the net upward force from the surroundings. Now, water doesn't float in water, and water doesn't sink in water. A chunk of water is just going to hang there motionless in the middle of more water. I mean, unless some fish goes by to stir it up or something like that. So this thing will be in equilibrium. Summation of the forces in the y direction equals 0. So therefore, the buoyant force equals the weight of that much water. Now, if the thing that's here is not water, if it's some other substance, like if it's a block of concrete, okay, well, that doesn't change anything about the surroundings. The upward force from the surroundings will still be equal to the weight of that much water. Concrete being denser than water, the weight of the concrete would be more than the buoyant force, so you let go of it and it heads for the bottom. On the other hand, if this was a chunk of some very low density substance like cork or styrofoam or something like that, then the weight of that block of styrofoam would be less than the weight of the water that would be there otherwise. The buoyant force is greater than the weight of the styrofoam, and when you let go of it, it heads for the surface. Okay, so this this makes Newton's laws sound like a recent development. This was discovered by Archimedes more than 2,000 years ago. And there's an interesting story that goes along with that, but I'll let you look that up. Supposedly he was sitting in the bathtub when he figured all this out. But Archimedes' principle says that the buoyant force equals the weight of the displaced fluid. If you're talking about a ship in the ocean, it equals the weight of the buoyant force that supports it equals the weight of the displaced water. If you're talking about a dirigible floating in the air, the buoyant force on it equals the weight of the displaced air, and so on. So as far as some sort of formula, because everybody always says, what's the formula? A little scribbling over here. Archimedes said, the buoyant force equals the weight which has been displaced. When you put the ship into the ocean, how much water gets pushed out of the way, okay? What's the weight of the water that would be there if the object you were talking about wasn't there. Well, I'm going to combine that with for the mass of the displaced water, mass equals density times volume. That follows directly from the definition of density, okay? Density is mass per unit volume, multiply both sides by V, m equals rho times V. So if you put those together, the buoyant force would equal rho V times G. But that can be a little tricky. Like if you are working on a problem that tells you both the density of the object and the density of the surrounding fluid, keep in mind that don't just throw random numbers at equations. Try to keep in mind what they mean. And what's lurking behind this equation is that you're calculating the weight of the displaced fluid. And if you're calculating the weight of the displaced fluid, it would be the density of the fluid that goes in there for rho. Not the density of the object that's doing the displacing, the density of the fluid would tell you the weight of the displaced fluid. As for the volume, if you were given a problem that tells you the volume, well, like this next one, you've got a rock that's underwater, and it involves the buoyant force on that rock. If the question told you the volume of the rock and also told you the volume of the water, it's the volume of the rock you want, okay? Because you're calculating the weight of the displaced fluid. Well, what's the volume being displaced? It's not, if you threw the rock in the Pacific Ocean, you don't want the volume of the Pacific Ocean. It's the amount of volume that's displaced that belongs in there. Okay, so one last look at the note packet. And I'll do the last example in the entire course, unless you want to count the problems that are on the review sheet that are the next couple pages after this, the review for the final. So you've got not a terribly large rock, 100 cubic centimeters. And if you weigh it on dry land, the scale says, now, even if you weigh it on dry land, you're not going to get exactly the true pull of gravity on it because there's a buoyant force from the atmosphere. But the density of air is something like 800 times less than the density of water. So the buoyant force from the air would be 800 times less than you would get from water. And compared to the weight of the rock, that's only going to affect like the fourth or fifth significant figure or something like that. And if you're not being super careful about your measurements, you don't need to worry about that. So we're going to say that the reading you get on dry land is the true weight of the rock, the true pull of gravity. But then you weigh it again underwater. You've got some sort of a scale that'll work underwater, and you set the rock on it. And what does it read there? So there's the rock sitting on the scale as it's being weighed. And there's actually 3 forces acting on it. The Earth's gravity pulls downward on it, which, as the question says, is 3.5 newtons. And there's the normal force, which comes from contact with the scale that it's sitting on. In addition, there's also the buoyant force, which comes from the surrounding water. The thing to realize, I think this has come up once or twice before at other points in this course, but a scale doesn't directly read the pull of gravity. A scale tells you how hard it's being pushed against. And so the scale reads the normal force. When the question says, what does the scale read? It's asking for N. The rock is in equilibrium. It's just sitting there as time goes by without accelerating. And so therefore, summation of the forces in the y direction, which is the direction of every force there is, the summation of the forces has to be 0. Both the buoyant force and the normal force point upward, so they're positive, and the weight, mg, pulls downward. So I've got 3.5 to stick in here. This is what I'm looking for. If I had a number for the buoyant force, I'd be all set. So the main thing to this problem is to figure out the buoyant force, which just kind of slide over a little bit. Do that over here. Buoyant force equals the weight of the displaced water, which would be the mass of the displaced water times gravity. Mass is rho times v. Fill in the numbers. To get the mass of the displaced water, you would use the density of water. Thousand kilograms per cubic meter. For the volume, well, it tells us the volume is 100 cubic centimeters, but cubic centimeters isn't going to cancel with cubic meters. Got to have, well, there's a couple of ways of doing that. One way of doing it is you could work in centimeters instead of meters. The density is 1 gram per cubic centimeter times 100 cubic centimeters means 100 grams. And then you could convert that to kilograms to get the force in newtons. That'd be one way to go at it. The way I've written it out here, conversion factor. 100 centimeters to the meter, but that's linear centimeters and linear meters. To cancel with cubic centimeters, you have to raise that to the 3rd power. There are 1,000,000 cubic centimeters to a cubic meter. So you have to move the decimal 6 places, not 2. And then we've got G on the end here at 9.8. So one way or another, you keep track of the units and get the decimals in the right place and all of that. The buoyant force comes out just under a Newton. So we've got that the normal force equals mg minus b, and that's the true weight, 3.5 minus the 0.98 for the buoyant force. So underwater, and of course, many of you are familiar with the sensation where you've been in a swimming pool for a while, and then you go to get out, and as you're climbing up the ladder, it's like, how did I get so heavy? I mean, did I just like land on Jupiter or something like that? Because you've gotten used to having your weight supported by buoyancy. Most of your weight, the density of a human being is a lot closer to the density of water than the density of a rock is. So you get in a swimming pool and almost all of your weight is being supported by buoyancy. Your muscles don't have to do much of anything. So it's going to read about 2.5 newtons. Okay, well, that's the end of this course. At the time I'm recording this, the decision has already long since been made that we will continue through the spring semester with the same sort of format that we're using in the fall. It's hopefully for the fall semester 21, we'll be able to get back to normal maybe, but it seems unlikely for the spring, so we went ahead and scheduled everything like the fall with the remote lectures. One difference from my point of view, I may have told you this story before already, but last fall of 19, I had begun recording before anybody had ever heard of COVID, I'd started recording all of my lectures. And just because, you know, there was starting to be a lot of talk about flexible formats for courses and all of that. And you know, what if somebody misses a class because they were sick, or even if they just don't want to come to class that day because they live an hour away and it's so much more convenient to just watch it on a computer screen, just, you know, come in for the tests and the labs. And so I started recording all of my classes at the beginning of the fall semester last year. And I got to the end of the semester. It's like, well, course is over, don't need that anymore. And I deleted them all, which is why I've been spending hours and hours and hours this semester recording things I had already recorded last year. But by the end of the spring semester, I had an entirely different perspective on such things, and I kept those recordings. So what I'm saying is, your instructor for Physics 132 will not be present day me, it will be last year's me teaching Physics 132, at least for the lecture part of the course. I have to record the labs for the earlier part of the semester, but hopefully we'll at least see each other on Fridays and we'll get to interact with present day me on Fridays, unless the virus flares up, and then we could really be stuck at home again, which I would not like. So anyhow, I guess the course is over and now I'm just rambling. So I am going to click end.